Hello friends, welcome in the online lecture of pericyclic chemistry. In the last lecture we discussed about the correlation diagram of 2s plus 2s cycloaddition reaction, and now in this lecture we have to see the 4s plus 2s cycloaddition reaction, in which this 4s system, this 2s system both interact with each other to form the cyclic product. This cycloaddition product is there. Now reactant orbital contain these 6 orbitals, 4 orbital from one partner and 2 orbital from another partner, and here this product molecule contains 6 molecular orbitals, 4 sigma and 2 pi molecular orbital. So this is about the reactant and product orbital. We have drawn reactant orbital. Their energy wise arrangement is done in this manner: psi 1 first, then pi, psi 2, psi 3 star, pi star and psi 4 star, 3 bonding and 3 anti-bonding orbital. Now in this case we have to draw the product orbital. So their energy wise arrangement is in the manner: so see, sigma 1, sigma 2 is the second orbital, then pi orbital, then pi star orbital, sigma 3 star orbital and sigma 4 star orbital. So this is energy wise arrangement for the product orbital. Now product orbital are here. Product orbital we have to draw one by one. Now sigma orbital, these sigma bonds are undergoes breaking. This bond, this one is the second bond. This bond undergoes breaking when we go reverse, or these bonds are formed. These bonds are formed here in this case. So we have to consider the bonding of these bonds. Bonding of these bonds. So here in this case, see, sigma 1 orbital we have to draw first. So sigma 1 orbital have to draw. We have to draw these orbital 4 pi 16. These are the orbitals, and this 2 pi electron system in which we have to show the bonding. Now this is M symmetry, plus minus plus minus. This is M symmetry but bonding. M symmetry bonding orbital. So it is bonding because sigma 1 is sigma bond form only when there is a bonding between the orbitals. So bonding orbitals are there. Here I draw plus sign, here plus sign. So bonding molecular orbital. See the second, how to draw second orbital. Here 4 pi 16, and this is 2 pi electron system. Now this is also bonding orbital. So bonding orbital have bonding, another possibility to form bonding orbital, that's C2 symmetry. C2 symmetry, so plus minus plus. This is C2 symmetry. Again another bonding to occur, there must be same sign. So plus bonding, minus bonding molecular orbital. So bonding molecular orbital here plus minus, C2 symmetry but bonding. Here pi, we know that pi, these are shown in the manner 0 node, 1 node, because in pi orbitals we count node first and then go for the orbital drawing. So no node, that is plus minus, and here 1 node, so 1 node shown here in between the orbitals, plus after node it becomes minus plus. Okay, so these are pi orbital drawing. See the drawing of sigma 3 star orbital. So sigma 3 star orbital drawing, here 4 pi 16, the end orbitals, and 2 pi 16. So this 2 pi 16 shown here, but it is anti-bonding orbital. How anti-bonding form? Here M symmetry, plus minus, and here M symmetry also, same symmetry, minus, same symmetry, but here anti-bonding orbitals are there. Anti-bonding orbitals, so it is anti-bonding. And last we have to draw, these are product orbitals. plus C2 symmetry but anti-bonding. So here C2 symmetry plus minus minus plus. So here both having C2 symmetry but anti-bonding, plus minus overlap, plus minus overlap. So opposite sign overlap is there, and due to opposite sign overlap, this shows anti-bonding. So first we have drawn all the product orbital, that is sigma 1, sigma 2, pi star, sigma 3 star, sigma 4 star. These are energy wise arrangement according to their symmetries. Okay, so sigma 1. Now what we have to check here? We have to check the symmetries. We have to check the symmetries, vertical symmetries, sigma V. So what is sigma V for each molecular orbital? That we have to write here. That we have to write each symmetry for the orbital here. So for orbital, sigma 1, sigma 2, for sigma 1, pass the vertical plane and fold the orbitals. What happen? Negative sign coincide on negative, positive on positive. That means same sign coincides, and when such situation occur, it is symmetric with respect to vertical plane. Second vertical plane we pass. It is observed that when we pass this plane, negative sign coincide on positive. That means opposite sign coincides, and it is asymmetric with respect to vertical plane. Here, when we pass vertical plane, then it is symmetric. When we pass here vertical plane, asymmetric. Here in this case, when we pass plane, it is symmetric, and here in this case, when we pass plane, it is asymmetric. Just check it. Pass the plane and fold the orbitals, plus overlap on minus, minus overlap on plus. That means opposite side overlaps, and when such situation occurs, it is asymmetric with respect to that particular plane. And here we have taken sigma vertical as a plane. So these are product orbital and their symmetries. These are reactant orbital and their symmetries. Now we have to draw the correlation diagram here by drawing again the reactant orbital and product orbital. I am writing here product orbitals, reactant orbital first, psi 1, here pi, psi 2, psi 3 star, pi, and psi 4 star. So these are product orbital. And then symmetries. We have to write symmetries. Yes. Then it is symmetric. It is asymmetric. This is symmetric. This is asymmetric. And again this is asymmetric. Asymmetric. Okay. So these are reactant orbital. We shown here. Now we have to draw product orbital. Which are product orbital? Sigma 1, sigma 2, pi star, sigma 3 star, and sigma 4 star. Sigma 4 star. These are product orbital. Now we have to write their symmetries. Yes, symmetric. Second, sigma 2. Sigma 2 is asymmetric. So asymmetric. Pi is again symmetric orbital. So symmetric orbital. Pi star is asymmetric. Sigma 3 star is symmetric, and sigma 4 star asymmetric. So these are product orbital. Their symmetries. Now we have to correlate the symmetries of reactant and product. But before that, we have to draw a line between ground state and excited state. So ground state and excited state, anti-bonding orbital and bonding orbital. We have drawn line between bonding and anti-bonding orbital. So this represent ground state, and the orbitals above the line represent excited state. Okay. So now start correlating orbitals. So here psi 1 having symmetric. So symmetric should be correlated with symmetric. Now again second symmetric correlated with symmetric. Here correlated with symmetric. Asymmetric should be correlated with asymmetric. Then symmetric correlated with symmetric. Asymmetric should be correlated with asymmetric, and this is second asymmetric correlated with asymmetric. So what is our observation from this diagram? From this diagram, this correlation diagram, it is observed that from correlation diagram it is observed that ground state orbital of reactant correlated with ground state orbital of product. Ground state orbital of reactant correlated with ground state orbital of product. Then this reaction is thermally allowed reaction. When there is no excited state reaction or excited state ground state combination, that reaction is thermally allowed, and here in this case only ground state combination, then such reaction is thermally allowed reaction. So this reaction we can show that psi1 contain 2 electron, phi contain 2 electron, and phi2 contain 2 electron. It simply correlates with sigma 1 contain 2 electron, sigma 2 contain 2 electron, and phi contain 2 electron. No excitation, no excited state combination. So 4s plus 2s reaction, 4s plus 2s cycloaddition reaction is thermally allowed reaction. And same result we have obtained previously in frontier molecular orbital method. In FMO method we have obtained the same result where the 4s plus 2s cycloaddition reaction are thermally allowed reaction always. So from that we have chosen selection rules here. So 2s plus 2s cycloaddition reactions are always allowed by photochemical mode of activation, and similarly 4s plus 2s cycloaddition reactions are always allowed by thermal mode of activation. So 2s plus 2s cycloaddition reactions are photochemically allowed, and 4s plus 2s cycloaddition are thermally allowed, which can be shown with the help of this correlation diagram. So this is about correlation diagram and cycloaddition reaction and correlation diagram. What we learned in previous lectures, that cycloaddition reactions are the reaction in which two or more unsaturated systems combine to form cyclic product, and the cycloaddition reaction can be analyzed by two ways. Here in our syllabus actually there are 4 ways to analyze this reaction, but here we are analyzing these reactions by 2 methods. First is FMO method, frontier molecular orbital method, in which we consider HOMO of one partner, LUMO of another partner, in which if the symmetries of HOMO and LUMO of reacting partner matches, then that reaction is allowed by that particular way, either thermally or photochemically. Second method of analysis is the correlation diagram. By correlation diagram we got to know these reactions are thermally allowed or photochemically allowed by drawing the reactant orbital, product orbital, their symmetries with respect to sigma vertical, and in 2s plus 2s sigma vertical as well as sigma horizontal. By considering those symmetries and correlating them, we know how the reaction is thermally allowed or photochemically allowed. From this we again reach to the conclusion that 2s plus 2s cycloaddition reactions are photochemically allowed, and 4s plus 2s cycloadditions are thermally allowed. So 2 topics in the pericyclic reaction we have completed. Now third topic that we have to start here, the sigmatropic rearrangement. Third type of pericyclic reaction is the sigmatropic rearrangement. Now in the sigmatropic rearrangement there is a transfer of sigma bond from one end to another end of within the same molecule. Within the same molecule the reaction occurs. So sigmatropic rearrangement. Third topic we have to see sigmatropic rearrangement. Third type of pericyclic reaction. Sigmatropic rearrangement. Now in sigmatropic rearrangement, see the example CH2, CH double bond, CH2. Actually it is CH3. So this hydrogen transferred from one end to another end with this sigma bond. That means this sigma bond or this group or atom. This is atom actually here, but sometimes there is a transfer of group also. So here this atom transferred from one end to another end with cyclic shift of electrons. So these pi electrons are shifted here. So this is cyclic shift. Cycle is completed here. So cyclic shift of electron is there, and due to this cyclic shift of electron, this reaction is under pericyclic reactions. Okay. So what is the result of reaction? CH2. This bond shifted here. CH2 double bond CH. Then this CH2 and this transferred hydrogen is here. So hydrogen transfer from one end to another end. So this is sigmatropic rearrangement. Now see how to name this sigmatropic rearrangement, by which notations or which numbers we are using while naming this sigmatropic rearrangement. So this is sigmatropic rearrangement in which atom or group of atom transfers from one atom to another atom. Okay. So this is the part where the chain or the group transfer from which this part is known as alkenyl chain. And this is the group which undergoes transfer. So group undergoes transfer. So we have to start numbering from the transferring group. So this group is undergoes migration. So this group is number 1. Also numbering 1 started from here. 1, 2, 3. So this group transferred from position 1 to position 3. So this reaction is named 1,3 sigmatropic rearrangement. This rearrangement is called as 1,3 sigmatropic rearrangement. Okay, 1,3 sigmatropic rearrangement. This is migrating group or migrating atom, and this is alkenyl chain. Migrating group, another alkenyl chain. Okay, alkenyl chain and migrating group. See another example. CH, here hydrogen is there. 2 CH double bond CH, CH double bond CH2. So this is sigmatropic rearrangement. This sigmatropic rearrangement in which this is migrating group and this is alkenyl chain. So start numbering from migrating group. It is number 1. This is again number 1. This alkenyl chain. 2, 3, 4, 5. Okay. So this migrating group transfer from 1 to position 5. 1 to position 5. So we obtain product CH2 double bond CH, CH double bond CH, CH2 and this migrated atom hydrogen. So in this case the group transfer from position 1 to position 5. So this is 1,5 sigmatropic shift. This shift is called as 1,5 sigmatropic shift. In this way we know how to name this sigmatropic rearrangement. Another example where CH2, CH double bond CH, CH double bond CH, CH double bond CH2. Now in this case, this is migrating group, migrating atom here in this case. So start numbering from migrating atom 1. This is again number 1, 2, 3, 4, 5, 6, 7. So now here hydrogen transfer from 1 to position 7, and there is a cyclic shift of the pi electrons, and we get the product here CH2 double bond CH, CH double bond CH, CH double bond CH and CH2 and this migrated hydrogen. So migrated hydrogen is from position 1 to 7, then this shift is known as 1,7 sigmatropic shift, or this rearrangement is known as 1,7 sigmatropic rearrangement. So this is about the introduction of sigmatropic rearrangement. Okay, thank you.